the speed of light in the second medium is less than speed of light in the first medium. There's obviously speed less than speed of light in air or vacuum. Yes, I will do that, Srishti. Notes and recording, both things I will share very soon. Okay. So we had seen Snell's law statement was that mu1 sine theta 1 is equal to mu2 sine theta 2, where theta 1 might be angle of incidence, then theta 2 is the angle of refraction, or could also be the situation where theta 2 is the angle of incidence, which implies that theta 1 becomes the angle of refraction. This is in general Snell's law. So let's look at a quick sort of geometrical application type of problem based on this. So we have, let's say, a transparent plastic slab refractive index of plastic is suppose 1.73 or about root 3. Okay. And we have, of course, air on either side. And the thickness of this slab is, let us say, T, which is, let's say, 36 centimeters. Now we have a ray of light which is incident over here like this, then refracts through this, and then again emerges like this. So, so given that the angle of incidence is 60 degrees, first thing is find R and E and show that the emergent ray is parallel to the incident ray. And then additionally, we have to also find out that if you use the incident ray forward like this, this ray is supposed to be actually parallel to this. So this perpendicular distance between them is d. So we have to find d. Okay. So start with this problem. We will discuss more important type of problems after this. So the emergent ray. So very simple calculation involving Snell's law first of all, and then a little bit of geometry you have to work out. Okay. Set some triangles, etc., by dropping some perpendiculars and all, and from that you can find the perpendicular distance between the emergent ray and the parallel, and sorry, the incident ray. Yeah, Ansh, we are just starting with this question. Before that, we have done a quick review of Snell's law and the concept of refractive index. That's the part on top. Yes, Aman, your answer is correct for R as well as angle of emergence. Okay. 12 root 3. Yes, seems correct. The final answer also seems correct. I'll have to just verify that one. Okay, just just a moment. Continue with the problem. I'll share the whiteboard again. Just give me a moment. I'll share the whiteboard again. So the angle of refraction should be coming to be 30 degrees by using Snell's law. Okay. So you take mu of air as 1. So 1 into sine I should be equal to mu of the plastic, which is root 3 into sine R, and put the value of I as 60 degrees. So you'll get R as 30 degrees. Okay. So from that, you'll also understand that the ray of light bends or deviates towards the normal by an angle of I minus R or 30 degrees. Okay, so that's another important concept over there. Now you use geometry there to understand that because the two refracting surfaces are parallel to each other, so the angle of incidence at the second surface will become the same as the angle of refraction at the first surface. Yes, very good, Jagannath. Okay, so you will get the angle of incidence at the second surface. Yes, and then again use Snell's law, but this time the incidence is happening from glass or whatever plastic. Okay. So first you solve this refraction, this one. So as I was saying, here this is the angle of incidence, this is the angle of refraction, because the direction in which the light ray is going is like this. So you can also understand that if you produce this forward, the incident ray forward, this will be what we call the angle of deviation. So that's an additional little concept you can add over here. Delta, this is the angular deviation. It's how much the ray bends because of the refraction. So anyhow, so this is mu is equal to 1.73 or approximately 3, and this is mu equal to 1. So 1 into sine I is equal to root 3 into sine R, and I is equal to 60 degrees. So this tells us that R is sine inverse of half or 30 degrees. So as expected, R is less than I because mu is greater than 1. The plastic is greater than. Okay, so now you use simple geometry to understand that the incidence at the second surface is going to happen at an angle of incidence which is equal to this R only. So if I take this as I prime. So you can see that I prime is equal to R only. And therefore, when I use Snell's law, you realize that this ray will emerge at some angle of refraction, which we can write as R prime. And that is the angle of emergence that we're looking for. So this time you can see that the deviation is going to be this. Let's produce this ray forward. So if I produce this ray forward again, you can see that there is a deviation delta prime like this now. Okay. So again, mu of plastic into sine I prime is equal to mu of air into sine of R prime. So here we have root 3 into sine 30 is equal to 1 into sine E. So we have that emergent angle will be 60 degrees. So now delta prime is R prime minus I prime, which is 30 degrees. Okay. But it's 30 degrees like this, whereas delta was 30 degrees like this. So first there's a clockwise deviation and then an anti-clockwise deviation. So the net angular deviation is 0. So you can see that after both refractions, let's write it as minus because it's clockwise, and then this with a plus sign because this is anti-clockwise. So the net deviation is 0, net angular deviation. So that's why emergent ray is parallel to incident. Now we have to find what we call the lateral deviation actually. So let's and use the diagram for that only. Yes, 12 root 3 or 36 by root 3, that is the correct answer for that small d. So let's quickly wind up this question. All right. So now to understand that this thing, we can do two constructions here. One is that we can complete this right angle triangle. Let's just call this point here A, this point here B, and this point here C. And therefore, let's call the hypotenuse as X and this base as, let's say, T. So in triangle ABC, you can see that T by X, or basically AB divided by AC, is equal to cos r. So that thickness was given to us as 36 centimeters divided by this hypotenuse is cos 30. So x becomes 72 by root 3 or 24 to root 3 centimeters. Okay. Now the next thing we can do here is we can drop a perpendicular from C onto this. Let's call this point D. So now you look at triangle ACD. Okay. So in my diagram, it doesn't look that way, but they actually should be congruent triangles because this is exactly bisecting this angle. Anyhow, so this whole angle is I now. 60 and this is 30, so this delta should be the same. But anyhow, so here if we take this perpendicular distance is D, so CD divided by AC is basically D divided by X. That should be equal to sine of delta, where delta is I minus R, or in this case 30 degrees. So D divided by X now, which is 24 root 3 is equal to sine 30. So D is equal to 12 root 3 centimeters approximately. So these kind of simple calculations are very much part of typically JEE mains, or for that matter, even your board syllabus. So this chapter will be part of your semester 2 exam in board, not semester 1 exam. So you have some time to prepare it for boards also. But some of the derivations will be important for boards also, and I will point out to you at the end of the chapter which ones you have to keep in mind for the board exam. Here we will focus more on the problem solving, the numericals. Okay, so let's move on now. Now, next thing we had looked at was that real depth apparent depth formula. So this is something very important from numerical problems applications point of view. Yes, I'll scroll up. Okay. Especially at the JEE advanced level, you can get some tricky questions based on this. So we'll discuss. Okay. But let's begin with the very basic discussion first of this. So if we have, for example, a fluid, some liquid which has a refractive index equal to mu, and on this side there is air which has refractive index equal to 1, and inside the fluid there is some point object O which is at an actual depth of small d here. Okay. And it is being viewed from normally above like this. So what we had understood is actually if you consider the paraxial rays, that is the rays which are nearly parallel to the principal axis. So first of all, if you consider like a ray which is actually along the principal axis, it will go undeviated. Or a ray which makes normal incidence, it goes undeviated. That is one of the things of Snell's law. So this observer's eye receives one ray which is coming directly like this. But now if you want to consider another ray which is very close to this one, so that will also be received by the observer. Then it seems that though it's little difficult to show in a diagram like this, but what happens is you have to consider a ray nearly parallel to this. It's making a very small angle of incidence. And it emerges also with the angle of refraction, which is nearly very small angle. So these rays are received by the observer's eyes. Let's say. Imagine these two rays are actually very close. So now for demonstration purpose, what we can do is we can show a ray which is a little bit far off, but actually that is not the type of ray we are considering. The type of ray we are considering is the one which I have drawn earlier. is very close to the principal one, or very close to the one which has normal incidence. So anyhow, you consider these kind of rays here. So basically what you want to do is you want to produce back the refracted ray. When you do that, it will meet the principal axis somewhere here, let's say. So that becomes like the effective object that the observer is seeing. So if we imagine the second ray is also actually very close to the principal axis, then this one will also emerge. I mean, this will also merge and produce back. It will appear to be coming from the same point, O prime. So if O prime is at an apparent depth of D prime, whereas the actual object was at a real depth of D, then we had seen that D prime was equal to D divided by refractive index of the fluid. Okay. So now we can generalize this formula for this one, where now we consider that if there are two refractive mediums, like not necessary that it's water to air or some fluid to air. So this is a medium which is having refractive index E, and this is a medium which is having refractive index B. And there is an object inside here, which is at a perpendicular distance from the interface, it is D. And there's an observer seeing this from above. Then the object will appear to be over here to the object, where this distance is D prime. And now the general formula is that D prime will be D upon mu of A with respect to B. So for example, if mu A is greater than mu B, then it means that D prime will be less than D. And this is the example I've shown here, because the rays will go this way. Because we have imagined the rays are bending away from the normal because B is having lesser refractive index than B. So we've imagined this, okay. But there can also be a situation if mu A is less than mu B, then what will happen? D prime will be greater than B. This is also possible. So we will look at the application of this a little carefully now. Okay. But the main thing is you remember this formula in terms of the refractive indices of both of these. Okay. So before you write this down, I'll just go back to the previous section once. People had to note down some things. Okay, Priyank, I will find those recordings and send them also of sound. Na? Yeah, I think a couple of lectures recordings are pending for uploading. I'll send them as soon as possible. Okay, so now come to this and note this down quickly. We'll quickly do a couple of applications of this next. Okay, Dhruv, but note this down quickly, or just make sure you understand the calculations. Okay. So now let us look at one important type of application of this. So we have water which has refractive index 4 by 3 or approximately 1.33, and air, yeah, I'll scroll up again, so has refractive index 1. Now there is, let's say, I've just shown with a point. So this is a fish is underwater at a certain depth d below the water surface, and directly above that there is a bird b. Just consider them to be point objects at a height h above. So given that the actual depth of the fish is 36 meters from the water surface, and the height h at which the bird is flying, that is, let's say, 45, or let's make it say 42 meters above the water surface. So we calculate the depth of the fish with respect to the bird as seen by the bird itself. And similarly, the height at which the bird appears to the fish with respect to itself. So if you just imagine the ray diagram for once, you will understand that the fish will appear to be at a closer depth than its actual depth with respect to the bird. So actually, with respect to the bird, the fish is at a real depth from it of 36 plus 42. So that is 78 meters, but it will appear to be closer because the ray is bent that way. Whereas when the bird looks up, the fish will, when the fish looks up, the bird will appear to be at a distance which is more than the actual height, more than 78 meters above it. Yeah, Shikhar, R prime and Jagannath, to first answer your question, magnifying glasses use lenses better. They use convex lenses at close range. So they produce highly magnified but upright virtual images. We'll be discussing thin lenses very soon today. Next thing after this will be thin lenses only. So you'll understand the working principle of a magnifying glass, or what we call a hand lens. Okay. I'll show you the question also again. But before that, Shikhar, going back to your question, R prime and I prime in that previous question, they were, for the second refraction, they were the angle of incidence and angle of refraction. So what is happening in this question is that back to back, there are two refractions happening. No? So there's one refraction happening at the point A. So that's the first refraction. So their incidence is I and refractive angle is R. For the second one, the angle of incidence is I prime. It's going from glass or plastic to air. So that refraction is happening at the second surface. So this is the second refraction. It is from plastic back to air. Okay. Whereas this refraction that we did, this Snell's law, this was for the first refraction. Point of incidence was A for this one. That is air to plastic. Is it clear now?
Yes, sir.
Okay, so this formula now has to be used in this question. Okay, give it a try. I've already given you a hint that to the bird, it will appear that the fish is at a real depth, at an apparent depth of less than the actual depth, which is 78 meters. The bird will appear to be, the fish will appear to be closer than 78 meters below. Whereas to the fish, the bird will appear to be further away. It will appear to be at a distance above it or at a height above it of more than 78 meters. Yeah, so Aman, now to actually find the depth of the fish with respect to the bird, to that 27 meters, you have to add the height h above also. But yes, otherwise your answers are correct. So we will use the formula only, but for demonstration purpose, I will just show you a diagram to understand this. So when you are observing the fish as a point object from above, so the observer is above, the rays of light as they go from water to air will tend to bend away from the normal. So the fish appears to be at a point like this of f prime, where let's say this depth now becomes d prime. So so this was the general formula where this is medium D and this is medium E. So B is always the medium of the incident rays and A is the medium of the refracted rays. So you have to keep that in mind. So here our D prime will be equal to D of D divided by mu of water with respect to air. So this will be the real depth, which was 36 meters divided by 4 by 3. So 27 meters. Okay. So now to the bird. The fish will appear to be over here. D prime of 27 meters. So it will appear to be at a depth Yes, Aman, that's correct. Devansh, that's correct. Now, when you reverse the situation and the bird becomes the object and the fish is the observer, then you will see that the rays coming from the bird as the object to the fish below as the observer, they will deviate in a different way. They will bend towards the normal. So they will appear to be coming from a point which is further back. So the bird is here at an actual height of 42 meters. And now your fish is basically the observer below at a depth of 36 meters. Now the rays of light will bend towards the normal. So when you produce them back, they appear to be coming from a point which is further back. So the bird now appears to be at a point like this. So this is like the apparent height from the water's surface it will appear to be. So here the formula will be h prime is equal to h of divided by mu of air with respect to water. So now this is our medium B and water is our medium A. So h prime becomes 42 divided by mu of A divided by mu of water. So mu of water into 42. 4 by 3 into 42. 4 into okay. So to the fish, the bird appears to be at height which is okay. So this is what happens as far as the vision of the fish is concerned. The fish will observe the bird as if it's at an apparent height of small. So make sure you substitute the correct quantities in the real depth apparent depth formula. Okay. In the real depth apparent depth formula, you are considering as the real depth as the position of the object behind the refracting surface, not the total distance from the observer. Okay. So here don't substitute the real depth as 42 plus 36, 78 meters. As far as the fish is concerned, the bird is behind the refracting surface, that is the air water surface, at a distance of 42 meters. So its real depth is 42 meters behind that surface. But its apparent depth becomes 42 divided by refractive index of air with respect to water. So that becomes 56 meters behind. Okay, so this is a very important application and important type of questions based on this. Okay, so please let me know if there's any doubt in either of these cases. It's very important to understand the application and how we have substituted what quantity in each of these cases for the formula. Okay, what is the real depth? What is the apparent depth? Therefore, where the object appears to be with respect to the observer. Okay, in the first case, see what is happening now. The fish F is the object and the observer is in air above. So the rays of light coming from the fish, they bend away from the normal. No? So the apparent depth of the fish from the water surface below, it appears to be the real depth, which is 36, divided by refractive index of water with respect to air. So divided by 4 by 3. So the fish appears to be at a depth of 27 meters below the water surface. So now to the bird, where it will appear to be, the bird itself is seeing the water surface 42 meters below it, and the fish appears 27 meters further below it. So it appears at a total depth of 42 plus 27, so 69 meters. Hope it is clear now. Okay. And same with the second case also, only in the second case, the refraction, the deviation is happening the other way, it's bending towards the normal. So it appears to be at a further distance rather than a closer distance. Okay, now next we look at a very important formula based on this concept. So this is not a standard formula in that sense, but for JE questions, you should remember the formula and its application. The next one we are going to discuss. That is the apparent shift in the position of a point object due to a glass or any refractive slab. So basically, it's like this real depth, apparent depth formula only, but applied twice, back to back. Okay. So for example, if we have a situation like this, this is a glass slab where the refractive index of the glass is mu, let's say, and the thickness of the glass slab is d. Now, if we have a point object somewhere here, and there is an observer who's viewing it normally. So again, the rays reaching the observer are paraxial. Then what happens is that the object appears to be, so to this observer, the object appears to be closer than it is actually to the glass slab. So for an observer viewing a point object normally, that means from paraxial rays through a refractive slab, delta x, that is the shift, is given by this formula, and we will prove this formula very soon. So the object appears to be here. So O is the actual point object, and O prime is the apparent position of that point object O as seen by the observer. And very interestingly, of the object's distance from the slab. So the amount of shift is independent of this. Or for that matter, even the observer's distance. It only depends on two things: the thickness of the slab and the refractive index of the slab. The larger the thickness and the larger the refractive index, the more the lateral shift will be, delta x. So this is a very, very useful formula when it comes to problems where there are layers of refractive mediums. So instead of solving individually the real depth apparent depth formula again and again, you want to make use of the slab concept, makes life very simple. But first of all, we'll prove this formula. In fact, this is given as one of our proof questions in HC Verma's solved example set. It's not given as a separate formula, you will see the reference part of HC Verma, but rather this formula you've been asked to prove it in one of the solved example questions. But having said that, it's a very useful formula to remember so that you can directly apply it in questions, which you'll be seeing next. So if you finish writing this down, you can start working on the proof of this. Okay. So the proof of this is based on a kind of a ray diagram where you can see that the rays of light suffer double refraction, once from air to glass and then again from glass to air. And they emerge in the same way like the problem we did earlier, parallel to the incident ray, but laterally shifted. So when you produce back the emergent ray, they will meet the principal axis at a point forward of the point O. So that distance by which it is forward, that is our delta x, and you can quite easily prove that that is given by this formula. Okay, so let's look at the two phenomena individually now. Okay, so let's say this was a point object. Yeah, I'll scroll up. Let's say this point here is A and this point here is B. And let's take this distance AB. Sorry, OA is X. So our first refraction is happening from air to glass. And then our second refraction is happening from glass to air. So when you produce this ray backwards, let's say it meets the principal axis somewhere here. And then when you produce this final emergent ray backwards, it meets the principal axis somewhere here. Let's call this O2. So this is our final image. This thickness here is D. So for the first refraction, air to glass, so we'll take mu B as 1, mu A as mu. So the object is O and the image is O1. So the apparent depth should be equal to the real depth divided by refractive index of air with respect to glass. Is that? So if this distance here is now x1, so x1 will be equal to x divided by this. So x1 will be equal to mu x. Now for the second refraction, glass to air, the object is O1. So the real depth is O1b, which is x1 plus d, or mu x plus d. And the image appears to be O2. So the apparent depth is O2b. Let's take that as x2 plus d. So apparent depth is equal to real depth divided by mu of b with respect to a. So the apparent depth here is mu x, sorry, it is x2 plus d, and that is equal to the real depth, which is mu x plus d divided by refractive index of glass with respect to air. That's this. So from this now we can see that x2 is equal to x plus d by mu minus d. So now our lateral shift this is the proof. So you have to understand the working of these two calculations, the first refraction and the second refraction, the application of real depth apparent depth formula properly with respect to the diagram. Please make sure you do that. So this derivation itself is like a practice in itself of the application of this concept. But having done the derivation, you should remember the formula for direct applications. Exactly. So Jagannath, when we have a series of refractions one after the other, or series of optical events actually, so in that case you can see that the first event's image will become the second event's object, and the second event's image will become the third event's object, and so on and so forth. Here we have only two events back to back. So the rays which are incident on the second surface of refraction, they are incident over here, these rays. यहाँ पे जो incidence हो रहा है, these rays are coming from O1. Okay, they appear to be coming from that virtual point O1, not from O. So that's why for the second refraction, the object is becoming O1. So that is the concept that we have to pick up here. Okay. Now, quickly we'll see the application of this kind of situation. So first of all, for example, if you have a situation where there is a combination of slabs, what would otherwise be very hard to solve, because you'd have to solve, in this case I'm making a combination of three slabs, let's say. So we'd have to solve three into two, six refractions back to back. But here we can solve it very fast by using this. So this is, let's say, plastic, which has a refractive index mu1 of 1.75, let's say. This is glass, which has a refractive index of, let's say, 1.5. And this is something else, let's say this brown glass, which has a refractive index of 1.8. And each of these have thicknesses which are like this. This one is maybe 9 millimeters. This one is maybe 6 millimeters. And this one is, let's say, something in between. So it's, let's say, 8 millimeters. And now there is a point object here, and it's being observed by somebody normally from this side, where this actual distance is, let us say, 24 centimeters. So find the apparent distance d prime of the point object as observed by the observer normally, that is using the paraxial rays, but through the combination of the three slabs. So in this type of question, you can see it can really save you a lot of time to remember this formula, because otherwise you have to solve 6 refractions. Okay. Because there's refraction from air to plastic, then plastic to air, then air to glass, then glass to plastic, then air to ground, crown glass, and then crown glass to plastic. So this becomes never ending. Okay. But here you can use the direct formula, and you'll see that the object appears to be here at a net lateral shift of this much, where you can just understand that the net lateral shift is the shift because of the first slab, plus the shift because of the second slab, plus the shift because of the third slab. So that will become 8 into 1 minus 1 upon 1.75 plus 6 into 1 minus 1 upon 1.5 plus 9 into 1 minus 1 upon 1.8. This will be the lateral shift in millimeters. So I'll leave you to complete this problem and the answer. I'll also scroll back to the previous diagram. A couple of people to take down the things.
So could you show the question for a second?
Yeah. This one, no? Or the previous one?
This one.
Okay. So I'm just scrolling back for a moment. I'll come back to the question again. Okay, Samar, the diagram is clear for the previous one now?
Yes, sir.
Okay, so I'm coming back to this question. Okay. So I have set up the calculation for you. You have to just complete the calculation. But what I'd also like you to do is later when you're revising today's chapter, I mean today's notes, you can actually do the calculation of this whole system the other way by solving 6 refractions. It will be very, very lengthy, but it will, so just assume some distances between the slabs and, take these distances x1, x2, x3, etc. And like that, use the real depth apparent depth formula 6 times. Okay. And from that, find the final position, and you'll see it will come out to be the same. And why we understand that we can do the calculation this way is because the lateral shift delta x was independent of the distance of the object or the distance of the observer. It only depends on two things: the refractive index of the slab and the thickness of the slabs. So whether we bring the slabs closer together or we move them closer to the object or closer to the observer, it makes no difference. Whatever the distance between object and observer, each slab will contribute to that lateral shift by a fixed amount, which depends on its thickness and its refractive index. Okay, so Aman, that's correct. So here the total shift will become how much? 8 into 0.75 divided by 1.75 plus 6 into this will become 1 minus 2 by 3. So that is 1 by 3. This is a simple calculation. Last one will be 9 into 0.8 divided by 1.8. 8 into this is plus 2 plus
4. 9.42.
so 6 plus 8 into 3 by 7. Yes. So about 9.43, right?
Yes, sir.
Approximately a shift of, so this is exactly equal to, there's approximately a shift of 9.43 millimeters or 0.94 centimeters, we can say. If we approximate to second place. So the apparent position will be at d minus delta x. So that's something like this. Okay. So you can imagine the amount of time it saves. Okay, this type of slab. Now, what we'll also see is another interesting type of combination question where slabs concept becomes important along with the mirror concept. Okay. So we have a concave mirror. This now. So what we are doing is we are keeping this concave mirror. So this concave mirror has a radius of, let's say, 90 centimeters. Okay. And what we have is from its pole at a certain distance, we have kept a point object. So the distance OP is equal to, let's say, 50 centimeters. Okay. So we want to introduce a glass slab made of glass of standard refractive index this, so that this is what happens, that light which is incident here like this. So in a question like this, often what is happening is what is given to you as data in the question is actually just the ray diagram. So the light emerges like this parallel. So the light emerges from the system parallel to the principal axis. So for that to happen, we have to find what should be the thickness of the glass slab. This is a very typical JEE advanced type of question, which just because it's JEE advanced doesn't mean it's very difficult to solve. It's just very conceptual. So we have to find the thickness so that this happens. Find the thickness D of the glass slab such that rays emerge from the system parallel to the principal axis. Let's say O is a small point source type of thing of light. Okay. Like a small LED bulb or something. Okay, Tanish, let me check your answer. So basically what we want is this quantity should be equal to, I think, 5 centimeters, right? No, I think the answer is 15 centimeters. The thickness should be 15 centimeters. Okay, so the hint to you here is that where should we put a source or a point object with respect to a concave mirror so that the light after reflection becomes parallel to principal axis? It should be at the focal point. Then the light will emerge from the system. Parallel to the focal point. I mean, parallel to the principal axis. So that is the hint over here. So this mirror is seeing the object through this. No? So it's seeing the object here. These rays are incident on the mirror. See. So this O prime should coincide with what? The focal point of the mirror. Yes, very good. Okay. So that's it. You don't have to do anything else. You have to just understand that the rays incident on the mirror should appear as if they are coming from the focal point of the mirror. Okay. So the condition for this is that the object for the mirror should be at the focal point of the mirror. Now the object for the mirror here, this is at O prime, that is the position of O as seen through the slab. Okay. So I hope my ray diagram is also making it clear why it is this way. Okay, so again, you can see that without the slab formula, you'd really be in trouble over here. So now the focal length, if I just talk about magnitude and all that, is 45 centimeters. So O prime should appear to be at this distance of 45 centimeters. So that's why my lateral shift should be equal to 50 minus 45, that is 5 centimeters. So now apply the lateral shift formula. So from this you will get D as 15 centimeters. So if you know what you're trying to do and you're clear with all these application methods, then geometrical optics is a topic where you can easily score marks and easily save time. So you can attempt more questions from the difficult chapters like electrostatics, rotational mechanics, electromagnetic induction, SHM, those type of chapters where the questions take more analysis. You can save more time from these questions and invest that time in those questions. Okay, so hope this question is also clear. Okay, now we move on to the next very important part of application of Snell's law and refraction. So now instead of refraction at a plane surface, we will look at refraction at a spherical surface. Suppose we have some situation like this where we have some kind of refracting surface or refracting material of refractive index mu2, and here whatever medium is there, this has refractive index mu1, and the center of curvature of this refracting surface is, let's say, here. The radius of curvature of this, so this is a spherical surface. This is acting as the interface between the two media, the refractive index mu1 and mu2. Okay. Now suppose we have a point object somewhere here and we are observing it from somewhere here. So where does that point object appear to be? Now here we cannot use the apparent depth real depth formula for the simple reason that it's not a plane refracting surface, it is a spherical refracting surface. In fact, the way the observer is looking into it, you can see that he's seeing a convex refracting surface. So we will have to, once again, in our diagram, we will draw rays which are quite divergent, but we will have to consider them to be paraxial. So for example, in this case, if we imagine an incident ray like this, for example, and if we assume that medium 1 is the rarer medium and medium 2 is the denser medium. So for a moment, we'll assume that over here. So this is the normal at the point of incidence. So this line is the normal. So this here becomes the angle of incidence. This here becomes the angle of incidence. So we assume that the medium mu1 is rarer than the medium mu2. So we bend away from the normal. So our refracted ray will be like this, such that now this is the angle of refraction. Okay. And when you produce the refracted ray back, suppose it meets the principal axis at the point I, so that becomes the image. Okay. So we'll do a very similar derivation to how we had done before for mirrors. We'll call this angle alpha, we will call this angle beta, and this angle gamma. And this point of incidence, let's call it, this is the pole P, so let's call the point of incidence as K. So now considering this situation, we can develop a relationship between the distances of the image I and the object O with respect to the pole in terms of all these other parameters by using Snell's law. So first of all, Snell's law tells us that mu1 sine I, oh sorry, in this case it is, actually I'll tell you for a particular reason, we will take this as mu1 and this as mu2. Because in the standard formula, what we do is we always take mu1 as the refractive index of the medium in which the incident rays are there, and mu2 as the one which has the refracted rays. So mu1 sine I is equal to mu2 sine R. So this is Snell's law, and this is our first formula. Now you can see that in this triangle OAC, we have alpha is equal to I plus beta, or I can be expressed as alpha minus beta. So this becomes our second equation. And further, if we take the triangle IAC, then we can see that gamma will become R plus beta. So this is our third equation. Now we use the paraxial rays analysis. So even though the rays are looking quite divergent, but just consider only the paraxial rays, the ones which are very close to the principal axis. No, see what is happening is the R is the total internal angle. That is, angle IAC is actually equal to R. This is angle IAC. And this one is the other interior angle, angle ACI. So their sum is equal to the exterior angle. Okay. There are other ways of expressing this also, but these are the convenient equations to use. Okay. Now for paraxial rays, that is rays nearly parallel to the principal axis. Alpha is a small angle, and once alpha becomes a small angle, it means that beta will also be small, gamma will also be a small angle, and therefore I and R are also small angles. All the angles in the figure are actually very small. Okay? So basically, you have to imagine a diagram in which you're considering the rays which are very close to the principal axis. Considering rays like this, very close to principal axis, slight amount of deviation, this kind of thing. So all these angles are very small. So because these are small, so sin I is approximately I and sin R is approximately R. Okay. So equation 1, we have mu1 I is approximately mu2 R. Okay. And then substituting from equation 2 and 3, we have mu1 into I, which is alpha minus beta, is equal to mu2 into R, which is gamma minus beta. So we have this relation that mu1 alpha minus mu2 gamma is equal to mu1 minus mu2 into beta. And again, because alpha, beta, and gamma are small angles, so we can take alpha as approximately arc length AP divided by PU, beta as equal to arc length AP divided by PC, and gamma is again approximately arc length AP divided by PI. So on doing these substitutions, this formula further becomes that mu1 upon PO minus mu2 upon Pi is equal to mu1 minus mu2 upon PC, or so this is the formula we are getting in terms of the distances. Now we'll also incorporate Cartesian sign convention into this. But before we do all that, just make a note of this section. Just go through the equations, how we have set them up. Especially in context of the diagram. So the method is pretty much similar to the derivation we had done for spherical mirrors. But here we are using Snell's law instead of law of reflection. So instead of I equal to R, we're using the principle that mu1 sin I is equal to mu2 sin R. And then we are using the small angle approximation. So sin I becomes I and sin R becomes R, like that.
Sir, what is the angle I?
Samar, this is not exactly lens formula, but we'll see the lens formula comes by application of this, because in a lens there are two refractions like this back to back. For example, if this is from air to glass, okay, at a convex surface, then a lens will have another convex surface on the other side, okay, or another concave surface, or even a plane surface or whatever, and there will be back to back refraction. Now, in if we use Cartesian sign convention, then here what is happening is that this side things are positive, this side of the pole things are negative. And in this particular diagram, what we had was the object was here, the image came out to be here, and the center of curvature was here. So we substitute u as positive of pi, we substitute v also as positive of pi, and we substitute r as, and write this as capital R now. This will be positive of pc. Okay. So this is position and not distance, because it comes with sign. Position of center of curvature with respect to pole. So this formula converts to mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r, where we understand that this is r, okay, with Cartesian sign, okay, and mu2 is the refractive index of the medium with refracted, whereas mu1 is the refractive index of the medium with the incident. So I will just quickly show you with another demonstration that this formula remains the same for a concave refracting surface also. This time if we have this kind of situation.
So I've got.
So the center of curvature of the refracting surface is somewhere here. This is the pole. And suppose we have an object here. So take an incident ray like this now. So now this is the incident angle. Okay. Now let's assume in this case that it bends towards the normal. Bends like this, let's say. So r is becoming less than I because mu2 is greater than mu1. So then the refracted ray has to be produced back. Meet the principal axis somewhere over here. So this will become the image. So again, we use the same sort of method that this is alpha, this is beta. This point of incidence is A, and this angle here is gamma. So this time we again have mu1 sine I is equal to mu2 sine R, which will become mu1 I is mu2 R. And then we have, in this case, you can see that R is equal to beta plus gamma. This is in triangle CAI. And I is equal to alpha plus beta. This is in triangle COE. So we have mu1 into alpha plus beta is equal to mu2 into beta plus gamma. So we have mu2 gamma minus mu1 alpha is equal to mu1 minus mu2 beta. So again we'll take alpha as beta as gamma as these. Okay. So we will get, on substituting this, get mu2 by PO minus mu1 by, sorry, PI is mu1 minus mu2 by PC. Okay. But this time when we incorporate Cartesian sign, we will be taking U as plus of PO, P as plus of PI, but R we will take as minus of PC. This is with Cartesian sign. So that additional minus sign that comes on the right hand side, that will make this formula again the same, that mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. So similarly, you can take variations of this, okay, by putting the object on the opposite side and viewing from the other side, and also different combinations of mu1 and mu2, which one is larger, which one is smaller. But every time when you incorporate the Cartesian sign convention, you will get a common general formula. Okay. So the common general formula for all refracting surfaces with Cartesian sign convention is this mu2 by V. Okay. And this will even give you your real depth apparent depth formula if you take a plane surface. So R is tending to infinity. So for a plane surface, so you can think of the real depth apparent depth formula of the plane surface as a special case of refraction at spherical surface, where the plane surface is having infinite radius of curvature. Okay, so eventually in some time we'll be utilizing this formula and this derivation for understanding the behavior of lenses also, and from that developing what is called lens maker's formula. That is how we calculate the focal length itself of a given lens from the radius of curvature of each side or each of the surfaces of the lens along with the refractive index of the lens's medium. Okay, but yeah, first we have to, I'll scroll up. First we have to make sure that we fully understand this derivation as well as the application of this formula in questions involving just simply a refraction at a spherical surface. No, this is not that better. This is refraction at a spherical surface. This is nothing to do with lens, Shikhar. Okay, this is a single spherical surface. So you see, you have, for example, a solid chunk of glass and air outside, and the bounding surface is for example, a convex surface. This is the first example, or it could be a concave surface, like the second example. Okay. So bending of light is happening through refraction at only one surface, but that surface is now spherical instead of it being a planar surface. So now I'm taking you through the first derivation once more. Come back to the second example also. Okay, so now when we incorporate the Cartesian sign convention, this is how the first case works out into this formula. And now if I take a variation of the first case, where instead of a convex refracting surface, it was a concave refracting surface. And also now I have taken the case where mu2 is less than mu2 is greater than mu1. Okay, so the bending is happening towards the normal rather than away from the normal. So your triangles change, those relationships change between Pi, OP, and PC. But when you incorporate the Cartesian sign convention, as you can see below, the general formula comes back to the same. So actually, there are 4 different cases that you can work out in this. Refraction at a concave surface going from denser to rarer, concave surface going from rarer to denser, then convex surface rarer to denser, and convex surface denser to rarer. I've taken 2 of those 4 cases, but if you try the derivation for the other 2 cases yourself also, you can convince yourself that with the Cartesian sign convention, your formula remains the same. The general formula always remains the same. So now let us look at a quick example question. So what I have is a solid sphere of glass. The type is like a solid spherical glass object. The refractive index of glass I'm taking as 1.5, and the radius of this thing I'm taking as 60 centimeters. Okay, I'll show the second part again, just give me some time. Okay, now what is happening is, let's say this is a diameter. The center of curvature is here. This is just an imaginary line, this diameter extended which I've drawn. C is the center of the solid glass sphere. On either side we have air. Now there's like a particle, or like a small speck of dust or a point object which is somewhere over here, and this is being observed by two people, observer A and observer B, who are viewing this point object normally. So a point object, like a dust particle, or it could even be a small air bubble. When you create a solid glass object, often if there's a defect in the process of blowing the glass, there will be air bubbles. So those can appear like small particles. So a small dust particle or air bubble P is at a distance, oh sorry, not P, it's O. I've labeled it in the diagram as O. Is at a distance OC equal to 15 centimeters from the center. Two observers, A and B, view that point object O normally, that is by paraxial rays from either side. Find the position of O with respect to the glass sphere surface as seen by each of them. So just take down this question. We'll understand the working of this, and while you are trying it out, I will take you back to the previous section also once if you missed out anything to write down. Okay, so first of all, I'm just sliding back to the derivation above in case anybody has missed any part there. Then we'll come to the solution of this. Okay, so let's come back to this question. So each case we will solve individually. Okay, so and we'll use the same Cartesian sign convention for each case. So for example, when I'm talking about the observer A who's on this side of the glass sphere, so the center of curvature is, let's say, here, and the point object is here. Consider this to be my principal axis. Now I will not actually use the ray diagram for solving anything. It's just to give you an idea about what's happening here. So any incident ray like this will, after deviation, go off away from the normal. So what we expect is that as far as any observer on this side is concerned, somewhere here should be the image. And this is the pole. So for observer A, now actually you have to imagine that the rays are very close to the principal axis. This is just for representation purpose. Okay. What you have to actually imagine is that we are talking about rays which are
Paraxial.
paraxial. So very close to the principal axis. So the rays which are like this, slight amount of deviation like this. But even that slight deviation, when you produce it back, these rays will not be appearing to come from O. They'll appear to come from this point I. So like that. Anyhow, so for A, with this sign convention, I will take U as plus of PO, which will be plus 45, right? We'll take R as plus of PC, be plus 60, and it is glass to air. So mu1 should be refractive index of glass of 1.5, and mu2 should be refractive index of air or 1. Okay. So V, according to my diagram, is plus of Pi. So I want to find this out. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. So 1.5, sorry, 1 by V, my mistake. 1 by V minus 1.5 by U, which is plus 45, is equal to mu2 minus mu1. So 1 by V minus 3 by 2, so that will become 15 into 2, so 1 by 30 is equal to minus 1 by 120. So 1 by V is 1 by 30 plus, sorry, minus 1 by 120. So 1 minus 4. So V will come plus 40. So this plus 40 over here means that you're seeing a virtual image. Because it is coming by producing back the refracted rays. Because the refracted rays appear to come from the virtual point I, which is 40 centimeters behind the pole. So that is the interpretation of this result now. Now, similarly, I want you to do the calculation for the second one. I will just draw the diagram and set it up for you. Okay. And you don't have to flip the signs or anything. You can keep just the position of the pole changes because now the refracting surface is over here. So for the second case, this is the center of curvature. Our point object is here, but the pole is now this point, and the observer is on this side. So you'll have to consider rays which are incident like this. So this being the normal, they will tend to bend away from the normal. So as they tend to bend away from the normal, something like this is expected to happen. So you have to do the calculation to find out where the image is. Yes, I'll just check the answers you are sending in. Just give me a moment. Okay. So this is the first case. Now we'll do the second case also for. Yes, very good, Naman. That's correct. Yeah, people, the answer will be, I think 600 by 7. So yeah, that
Yes,
is
sir.
87, something like that. So anyway, the thing I want to concentrate here on is how we apply the sign convention correctly. So I'll just go through this carefully a little bit. So the thing is now, because the diagram is flipped, but we don't need to change the sign convention, or we don't need to flip the sign convention. We can still use the same sign convention, that this side is positive and this side is negative. Only our interpretation will become different now. Now, if V comes out to be negative, it means it's a virtual image because it's behind the surface as the observer is seeing. Okay. So according to this, we will take U as minus of uh, PO, which now will become how much? Minus of 60 plus 15. So minus 75. Okay. And we'll take R as again the position. So minus of PC. So that will become minus 60 centimeters. Okay. And V, according to my diagram, it looks like it should be something like this. Okay. Of course, we have to verify from the calculation, because if it deviates too much, it can also happen that it gives you a real image. But in this case, that will not happen actually. We will get a virtual image only. So according to this diagram, my V should be minus of PI, which is what I want to calculate. And again, it is a refraction happening from glass to air. So I should take mu1 as 1.5 and mu2 as 1. So mu1 by V minus, sorry, mu2 by V minus, mu2 by V minus mu1 by U, which this time will be minus 75, is equal to mu2 minus mu1 by R, which this time will be minus 60. So this is the full calculation. So let's see what this gives us. 1 by V plus हो जाएगा ये 3 by 2 into 75. So 2/3 of 75 is 50. So plus 1 by 50 is going to be minus by minus. So plus 1 by 120. So 1 by V will come out to be 1 by 120 minus 1 by 50, for which we can take minus 1 by 10
That is what.
common. So we'll get 1 by 5 minus 1 by 12. So minus 1 by 10 into 7 by 60. So V as expected is negative, but more importantly, it's a large negative value. So it is minus of, so something like this. So again, the interpretation is that this is a virtual image I, which is 85.7 centimeters behind the pole, as seen by the observer B. Yes.
No.
So this is something that you have to become competent at and understand carefully how to do these type of calculations. Okay, now let us move on from this to the very important part about lens maker's formula, which comes as a direct application of this actually. So lens maker's formula should not be confused with the lens formula. The lens formula is the UV formula for the lens, but lens maker's formula is the formula that gives us focal length of the lens, the value of small f, and then we use that focal length in the UV formula. Okay. So lens maker's formula is the calculation of focal length of a lens for a thin lens from its physical properties. So the physical properties are basically the shape, which is numerically the radii of curvature for its surfaces, and the refractive index of its material. So these two physical properties of a lens. So first of all, what is a thin lens? It is a refractive optical medium bounded by two spherical surfaces such that their poles are near. That is, it's a thin lens. So by near, we mean that the thickness is very small compared to the radii of the surfaces. So for example, we can have a biconvex lens whose two surfaces have center of curvatures here and here. So if this is surface 2, this is its center of curvature. This is the pole of the surface. Whereas if this is surface 1, this is its center of curvature. And this is the pole of surface 1. Okay, so the thickness of the lens should be very small. So then we can take, so the thickness, say d, equal to that distance p1, p2. D is very small compared to R1 or R2, where R1 is P1, C1, R2 is P2, C2. So this is an example of a biconvex lens. Similarly, you can have, for example, a biconcave lens. Where if this is surface 1, then its center of curvature is here, pole is here. If this is surface 2, where its center of curvature is where its pole is. So again, this all applies to it. Similarly, you have other varieties of lenses, like you have plano-convex lens. Plano-concave. You have concavo-convex. So on and so forth. Okay, so now to understand how refraction of light works with one of these. So for example, suppose we have let's take the example of of a biconcave lens. Then we will generalize the formula later. Glass lens, refractive index 3/2, suppose. Now this surface has a radius of, let's say, 60 centimeters, and this surface has a radius of 90 centimeters. And what we are doing is we are keeping a point object here, and because it's a thin lens, so we will consider the midpoint of the two individual poles as the lens's pole. Okay, so if the point object O is at distance OP equal to, let's say, something, let's say maybe 75 centimeters, want to find the position of final image. So what we'll do is we'll understand this as two back-to-back refractions at spherical surfaces. And we'll use the same sign convention and same everything for it. So we'll consider the first refraction air to glass. So mu1 is 1, mu2 is 1.5. That is glass's refractive index at surface 1. Okay. So using the Cartesian sign convention, the radius of curvature we will consider is R1 for surface 1. It will be minus 60 centimeters. You can see that the first surface's center of curvature will be this side. The second surface's center of curvature will be that side, and we take this as negative and this as positive. Okay. So, and for this surface, the object is O. So the object distance will be minus of OP. So we will take U as minus of 75. Now the image I1 we want to find out. So we'll take V as V1, which we want to find out. So now let's apply the formula mu2 by V minus mu1 by U. So I'm going to write it actually first this way. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. And then I'm going to substitute the values. So this is my equation 1. On substituting the values, I'll get this as 1.5 by V1 minus 1 by minus 75 is equal to 1.5 minus 1 by minus of 60. Right, so let's see what this gives us. 3/2 V1 plus 1 by 75 is equal to minus 1 by 120. So this will give us V1 equal to, let's just check. So 3 by 2 V1 is equal to minus of, so 5. Okay, so V1 will be pretty close to minus 45.
It's 1 by 8 plus 1 by 5, right?
Hmm?
Then this above step minus 1 by 15 in the bracket it's 1 by 8 plus 1 by 5.
Oh, sorry, I have taken 15 common now. Yeah, to recalculate this here. Correct. It should be 1 by 5. Okay. Make this correction. So what do we have now? We have 40, and the numerator we have 8 plus 5, 13. So this becomes,
Sir, 3 by 2 V1 is equal to 13 by 14 to 1 by 15.
3 by 2 V1 is this. So 2 V1 by 3 will become minus of 15 into 40 by 13 is 20. So V1 is almost this. So be a little more than 75. No? Little less than 75. No? So about 69 point something. But actually, for the final answer, we won't need to do this calculation also. So anyway, so what we'll understand in this ray diagram is that this is showing us that this ray of light is supposed to bend at this surface. Now we will not produce it all the way forward. Okay, because now it's also after bending, it's incident on the second surface. So if you produce this back, oh, so it is bending. Sorry, my mistake. It's not bending this way. It's bending towards the normal. Bend in a different way. So this will now bend something like this. So when we produce this back, this is giving us an image somewhere here. This image is I1. Now this becomes the incident ray for the second refraction. So I1 becomes the object for the second refraction, and then it will bend further away from the normal. So this goes like this. Introduce that one back. Let's say this is I2. So this is going to be our final image. So I'm coming to that second part. So this is, we have solved the first refraction so far. So the refracted ray inside the glass, in between the two surfaces, it appears to be coming from I1, which is at this kind of distance. Okay. So now let's come to the calculation for the second refraction. So this is the first refraction's answer. Now the second refraction, this is happening from glass to air. So this time we will take mu1 as refractive index of glass and mu2 as refractive index of air. Okay. And it's happening at surface 2. So the radius R2 for that we'll have to take as plus of what was it, 90 centimeters. Okay. And for this the object will be I1. So the object distance we should write as B1, which in this case is, and the image I2. So V is equal to V2, but that becomes the final image. So when we apply this, we have mu2 by V minus, we'll just write this as final image position. Write that as V. So mu2 by V minus mu1 by U, U is V1, is equal to mu2 minus mu1 divided by R, which is R2. So this becomes the formula for the second surface. So if you, without doing the numerical calculation first, if you just combine these two, equation 1 plus 2, you'll see we get a UV formula. This V1 term cancels out and we get, so if you take this term common, you see you're left with 1 by R1 minus 1 by R2. So you can write it like this, that 1 by V minus 1 by U is equal to refractive index of glass with respect to air. And later we'll see that the quantity on the right hand side is 1 upon the focal length of the lens. So V is the position of final image I2 basically. So anyhow, if we were doing the calculation here, we'd substitute this as 1 by V minus 1.5 upon minus 69.23 is equal to 1 minus 1.5 upon plus 90. So we'd solve for V from this, how much we get. So actually from this equation, you can see that 1.5 upon V1 is actually equal to minus of 1 by 75 plus 1 by 120. So it is minus of 13 by 600. Okay. So if you substitute that here, this becomes from this we can find the position of the final image. Close to something like this. So you'll just take 2-3 minutes more to complete this part.
Minus 13 by 18. 1 by V.
So we will get approximately minus of 36.73 centimeters. So again, this is showing you that it's a virtual image because the refracted rays which are emerging out of the lens are diverging in nature. You have to produce them back to, so look at the interpretation of that also. But more importantly, from this equation 1 and 2, the general ones that I've written, you see we get a general UV formula where we have to just substitute R1, R2 with the proper algebraic sign and U also with the proper algebraic sign. And every time for any shape of lens, as long as it's a thin lens, whatever the value of R1 and R2 with whatever algebraic sign, it gives us the formula for UV. So that is the lens maker's formula, and we convert that lens maker's formula into a formula for focal length by taking U at infinity.
अब इसको कंसंट्रेट करना
और ये हमारे अध्यापक पढ़ाते हुए
Okay. So now see the general formula that we get from here, which is the more important thing for us, which is applicable to any shape of lens and all that. Is that whether we have this type of lens or this type of lens or whatever be the case, if an object is kept on this side, then this is surface 1, which will have a radius of curvature R1 with proper sign. And this will be surface 2, which will have a radius R2 again with sign. Okay. So whatever is happening, the final position of the image will be at such that 1 by V minus 1 by U will be equal to mu of glass with respect to air minus 1 into 1 by R1 minus 1 by R. This will always come from the fact that at the first surface, we'll have the formula okay. And at the second surface, so when you combine these two, you will get this. So for example, in this case, R1 will be positive, R2 will be negative, because it's a biconvex lens. Whereas in this case, the object is here. This is surface 1. R1 will be a negative quantity. This is our surface 2. R2 will be a positive quantity. Okay. Yeah. So this formula, now in this formula, we can see that for U tending to infinity, that is parallel incident rays, okay, V becomes F, that is the position of image is defined as the focal point F, and F is the focal length, that is the position of F with respect to the pole. Okay. So that is this kind of situation. The rays of light are parallel from infinity, and if they are converging to a real focal point, this is a real focus because it's a converging lens. And if it's a diverging lens, there will be a virtual focal point because the rays after refraction will diverge. So virtual focus for a diverging lens. So anyway, so when we substitute this in the above formula, we get what is called the lens maker's formula. So substitute this in above formula. We get 1 by F is equal to Okay, so this is the lens UV formula, and this is the lens maker's formula. So for example, if you have a symmetric biconvex lens with radius of each side, let's say 60 centimeters, and refractive index of glass with respect to air, let's say 1.6, okay, then we'll have, so if we consider light coming from this side, we have to consider the first surface is center of curvature here, and the second surface is center of curvature here. So we'll have to take R1 as plus 60 and R2 as minus 60. So 1 upon F, which is this, with proper sign convention. So that means parallel rays here will converge to a point like this over here. So it's a real focus. This is a converging lens of focal length 50 centimeters. Okay, so this is the proper interpretation and application of this thing, the lens maker's formula. And now if you keep some object with respect to the lens at a certain distance, you can use the UV formula to find the position of the image. Position and nature, whether it is virtual, real, etc. So this is the most important part of your geometrical optics for both mains and advanced. The application of spherical mirrors formula, lens maker's formula, refraction at spherical surface, and combination type of questions involving slabs, etc., which we have discussed a few today. So next session we will look at more application examples with thin lenses. Okay. Numerical examples of the application of this UV formula and all that. We are mostly done with the theory part. Just few things remaining, like concept of critical angle in refraction, and then also prisms, the refraction of light due to prisms, and again there also critical angle and total internal reflection will come into play. And then the working principle of microscope and telescope. as optical instruments. But other than that, so next session mostly will be problem solving along with half an hour to 40 minutes to complete these remaining theory parts. Okay. So that's it for today's session, people. Wish you all the best and have a nice day.